Okay, we've seen how welds do under simple loading conditions when there's just a load that's parallel or transverse to the weld but acts right through the weld's centroid. That's actually the distinction, is that the forces that we've had before have acted through the weld's centroid. But what happens when we have a moment as well, or when we have a force that's applied such that when it's decomposed about the centroid into a force in a moment, well, there's a non-zero moment there. What do we do then? That's what we're going to learn, and we'll do it through an example. So here we have a steel bar that's 6 inches long. It is 3/8 of an inch thick and has 3/8 inch fillet welds. If the force were applied in this direction, then and it was straight through the center here, then it would pass through the centroid of the weld, and so we'd just call it a parallel fillet weld, and that would be a parallel loading. But now we've got a force that's applied at the end point, and it's going downwards. It does not pass through the centroid of the weld, and so that force turns into not just a force. If you look at the reaction forces that you'd need here at the centroid, you'd need to have both a force and a moment for static equilibrium to hold. So let's solve this one. The first step is to determine the location of the centroid and the direction of the surface normal of that weld pattern. So here's our problem, and I will just draw it right on the diagram itself. The centroid of the weld, you could be real careful about it. Sometimes there are more complicated shapes for which it's not so easy to determine the centroid. But you know how to do that, and you can also look up in tables in the Shigley book where the centroid is located with respect to the weld pattern. But I know that it's just centered this way and centered this way, so the center is right here, the centroid's right there. I'll go ahead and make up a coordinate system just to help us keep things straight in the problem. I'll call this X, this is Y, and this is Z. And this is our centroid. We'll call that O in this case. And the surface normal is in the Z direction. It's perpendicular to the plane of the weld. Okay, so that was step one. Step two, decompose the applied load into force and moment components at the centroid of the weld. All right, so what we need to do is determine what forces and moments that could be applied here would make for static equilibrium with this applied force. So let's go ahead, and I'm going to draw that coordinate system again, but I'm going to do it from the XY plane. I'll draw our part. I'm going to draw our part as though it's a lot skinnier. It doesn't really matter. And we've got an applied load. Here's our F. And this here is our point O. And we want to find what forces and moments would cause this to be in static equilibrium. Well, we could draw all the different possible forces and moments, but I'm going to stick with the two that I know are non-zero. You can see that we're going to need a vertical reaction force of some kind. I'll call that one V. And we're going to need some sort of moment here. I'll call it M, about 0.0. So that's what I mean when I say decompose the applied force into a force and a moment. It's whatever force and moment would be applied at the centroid to keep this thing in static equilibrium. And we can solve for the magnitudes. We can sum the forces in the vertical direction. That's positive V minus F is equal to 0 for static equilibrium, so V is equal to F. And the sum of the moments, about 0.0, well, we've got our moment that we applied, the reaction force. We've got the reaction force minus this distance here. That's 6 inches. This is a 2-inch wide weld. The center is at 1 inch in the X direction, so it's 6 minus 1, that's 5 inches. Let's come up with a variable for that. I'll call that length LO, and I'll call this point A. So that'll be LOA. So LO to A, and that's minus because we've got this force and it's acting in the clockwise direction times that force. And that has to equal 0, so that means that our moment is equal to LOA times F. And our force, the magnitude is 5,000 pounds. And the moment is 5 times 5,000 pounds, that's 25,000 pounds, inch pounds. I think that's step 2. Missed that, but as a review, equivalently, what reaction forces and moments about that centroid would the weld have to transmit for there to be static equilibrium? 3. Determine what kinds of primary and shear stresses that they cause. So here are the different kinds of primary and secondary. We call them shear stresses. We pretend that all the stresses in a fillet weld are shear stresses. And it turns out that we get to pretend that they're vectors too, instead of tensors, which is really handy. Forces cause primary shear stress component that we call tau prime. We label it tau prime. Moments with the axis aligned with the surface normal of the weld pattern are considered to be torsion, and they cause a secondary shear stress that we denote tau, subscript T for torsion, double prime. We call it secondary. Primary is from forces. We call it tau prime. Secondary is from a moment. We call it tau double prime. And the reason why we need the subscript T is because we could also have the moment is aligned with the axis that's perpendicular to the surface normal of the weld pattern, and we consider that to be bending. And we call those sorts of secondary shear stresses tau double prime subscript M. So let's see what we have here. We have a force, so V will cause a primary shear stress tau prime, and M will cause, well, M is about an axis, Z, and that is aligned with the surface normal of the part, Z. So according to our rules, or the convention of what we call these things, the moment axis, Rm, is aligned with the surface normal of the weld pattern, and so we consider it to be torsion. So I'm actually going to relabel our M as T, just to help us keep things straight. All right, so that's the kind of stresses that we're going to have. Next, we need to draw fields that correspond with those primary and secondary shear stresses. At each point along the weld, we want to draw the stress components as though they were a vector. The reason was we need to visualize the directions to see which ones will add up with one another. So step 4, what I'll do is I'll first draw the weld pattern. And there's a little guidance in this document about how to draw these fields. The primary shear stresses act in the direction of the force that caused them, and the magnitude is equal at all points along the weld. So how do I draw that? We're saying we're going to draw this primary shear stress for several points. It acts in the direction of the force that caused them, so it acts downwards. And they're all equal in magnitude. Same down here. So this is the component that's coming from V. And then we're also going to have a field that we're going to consider to be adding up with this. That's coming from our torque T. What does that look like? Secondary shear stresses, well, the bending type. We've got a torque type, so we can just learn about this in the meantime. They act in the direction you'd expect based on your experience with beam bending. We'll see an example of that next time. So that's going to be into or out of the weld plane. So that means, I can just explain it in this context, if instead this force had gone out of the plane here, right? You can imagine that's going to try to tear up this side of the weld, and this side is going to pull down back at it. So it's going to stay in contact, and it's going to put this part of the weld, it's going to be shoved up against the gray piece that it's attached to. So we would draw, what we draw is along the weld we'd have out of plane shear stresses if this force were acting in this direction. So if this force were acting in this direction, then we'd get these out of plane stresses. And they'd be very much like when we've analyzed beams before, we'd have the same sort of thing down there. That they'd be linear in their magnitude away from the centroid in this direction. Right? So the ones that were greatest in magnitude would be at the extremes, and then as you get towards the center, they're going to get smaller in magnitude as I've drawn. All right, let's undo all that, avoid cluttering our drawing. So the magnitude is like my over I. It's linear in y, the coordinate from the weld centroid to the point. In our case, it was x coordinate, but same idea, just different labels. Torsional secondary shear stress, that's the one that we're interested in. They act in the direction that you'd expect based on your experience with torsion. It's perpendicular to the vector from the weld centroid to the point that we're studying. So we're studying all the points, and so we're just going to keep on drawing. So let's say we're studying this point. Then the radius from our centroid there. So this shear stress is going to act in a direction that's perpendicular to this radius between the point that we're analyzing right now and the centroid. And so you can kind of see this force is going to cause this to twist around. So I kind of think about it, well, if I were at this point and I was twisting around, in what direction would I fly off, right? It's going to be in that direction, tangential in the direction that you're turning around. So it'll be in that direction. And here, it's going to be in this direction, and here. And these are slightly different in magnitude. It says the magnitude at each point is linear in r, the distance from the weld centroid to the point. So these are all different distances away. Well, I think we can just calculate them just to see here. This is a 1-inch distance here, and this is also 1 inch. We neglect the thickness of the weld when we're determining how far away it is. So we take the closest point. That's going to turn out to be conservative. Not because the radius is smaller in TR over J, but J is going to end up being smaller. Okay, so this one is a radius 1 inch away. And this one over at the top right, this radius, that's the square root of 2. 1 squared plus 1 squared is 2, square root of that, square root of 2. So this one is going to have a larger magnitude. This is about 1.414, so it's about 40% larger in magnitude than this one. You don't have to necessarily represent that accurately with their drawings. In most problems, you'll see where we're going. It doesn't matter too much, but it could. So just keep that in mind, and you'll be able to decide whether it's important to draw carefully or not. Then we want to determine the critical point. Where is this thing going to fail? If it's going to fail, where will the stress components sum as if they were vectors up to the highest magnitude? We're looking for places where the secondary shear stress are highest magnitude typically, so often further from the weld centroid. And we also want to consider places where the torsion secondary shear stress direction aligns with the primary shear stress. You know that the moment secondary shear stress can't really align with the primary shear stress in many cases, because often, just as you have a load on a beam, the normal stress and the shear stress are in 90 degrees to one another. They're not in the same plane. These are just some tips, right? Ultimately, we're answering the question, where will the stress component sum to the highest magnitude? That's the rule here. And if you can't choose just one point, if you can't guess, choose multiple candidates and analyze each. We're only going to do one because in this example, it's pretty clear. I can take a look at the corners. That's a good place to start. It's not always the place where it's going to fail, but it's a really good place to start because the corners are where the shear stress due to the torsion is of greatest magnitude because it's got the biggest radius. And it also so happens that they do add pretty nicely with the primary shear stress, right? So why wouldn't I pick a point here? Well, the torsional secondary shear stress is got a component that's acting upwards, and that's going to partially cancel out the downwards primary shear stress component here. We want a place where they add. And so one of the better places would be the right side, the top and the bottom, either one. This downward primary shear stress is going to add with the downward component of this secondary shear stress. Or if we were adding here, this primary shear stress acting downwards will add with the downwards component of this secondary shear stress. They're going to be completely perpendicular, say, at this point. This one's acting down, this one's acting to the left, so we don't get any amplification. Plus, this is of a lower magnitude to begin with. So it becomes pretty clear that you can pick out either one of these two as the critical points. Because first of all, they've got the greatest magnitude to begin with for the torsional secondary shear stress, and they've got components that add up with our primary shear stress. We don't have to analyze them both because they're going to have the same magnitude. I'll pay attention to this one up top from now on. Then determine the primary and secondary shear stress magnitudes from the forces and moments. So our primary shear stress magnitude, tau prime, that's given by V over A, the force divided by the area. Real simple. Well, V in our case is 5,000 pounds. That was the reaction force that was needed at the centroid in order to put everything in static equilibrium, and we could divide by A. So our area of the weld, and remember, we're still pretending that the fillet welds are going to fail along that minimum cross section. So we're cutting this thing here along the throat. I'm going to separate the two pieces, the gray from the blue, and cut the weld in half. This is that minimum cross-sectional area. And so the dimensions of that, it was h times W2, but we need to multiply by the square root of 2 over 2, 0.707, because that's the ratio of the throat to the leg size, h. 0.707 h times W2 in our case. That's 0.707 times 3/8, 2 inches. But wait a second, we've got two of them. Careful now. We have this one here and this one here. And if you're ever going to make that mistake, you can also look it right up in the table, and that'll help you not make a mistake. So table 9-1 is the torsional properties of fillet welds. Make sure you use the right table. There's a similar looking table for moment properties. It says the area is 1.414 HD, so twice 0.707 HD, where this is, H is the leg size, and D is the length of each of these welds, and that's our W2. So it's actually 2 times this, 1.0605 inches squared. That gives us a stress of 4,714.76 psi. Now we need to find what is the magnitude of the torsional secondary shear stress at the point that we're analyzing, this one right here. Torsion secondary shear stress is TR over J. TR over J, that means we need to find what J is. We can also find J in the book, but it's tabulated as JU, which is normalized by the throat thickness. So we'll see how to correct for that. JU is D times 3B squared plus D squared over 6. And we need to be careful in general to get our B and our D correct. In our case, it's 2 inches long and it's 2 inches separated between them, so we don't have to be super careful. For us, B and D are both 2. But in general, you need to be careful to look at the geometry. And this is JU. We'll see why that's important in a second. D times 3B squared plus D squared all over 6. So that is 2 times 3 times 2 squared plus 2 squared all over 6. That's 5.333, and that is, what are the units here? D and B squared, D and D squared. This is inches to the third. I mentioned it's normalized by the throat thickness. We need to turn our JU into a J before we put in this equation. This equation says J, not JU. J stands for unit, per unit throat thickness. J is, well, we don't need this right now, but this is helpful, that the tau double prime from the moment is my over I, as you might expect, but A is tabulated directly, so we looked it up in the table. J is root 2 over 2, 0.707 times H times JU. Turns out that 3/8 times 5.3 repeating is 2, so we get 1.414. Or actually, it's root 2. And this is now in inches to the fourth because we've multiplied by H. So let's calculate this magnitude. This was 25,000 inch-pounds times a radius. What's our radius here? Well, we already determined it was root 2. And on the bottom, our J was actually root 2 as well. Works out nicely to 25,000 psi. Back to the slide, IU is tabulated similarly. That's when we need to solve for moment secondary shear stress. We don't have that in this problem. Then we add the primary and secondary shear stresses as though they were vectors and calculate the magnitude. So tau prime is the magnitude of this here. That has magnitude 4.714 KSI. And this has magnitude 25,000 PSI. So we need to add those two as though they were vectors. So we can think about it like tau prime, well, that is 4714.76 PSI. And that's in the negative j hat direction if we were to draw unit vectors I hat and j hat. So we've turned that into a vector. And then tau double prime sub t, that is, well, we've got the 25,000 psi, but what component of that is to the right and what component is down? Well, we just have the hypotenuse is 25,000. We've got this is the sine and this is the cosine, but they're both of 45 degrees. This is 45 degrees because it's perpendicular to this, right? And this point over here, well, we've got 1 inch and 1 inch. We know that it is 45 degrees up from horizontal. 90 degrees from that is 45 degrees. And the sine and the cosine of 45 degrees, they're both root 2 over 2. Lots of root 2's over 2's. So root 2 over 2 is 1.414. 25,000 times 1.414 acting in the positive I hat direction to the right, minus we've got a 25,000 times 1.414 in the j hat direction, or it's acting in the same direction as this. We're going to add these two components. Doing the math on this one here, this is 17,677.67 in the I hat. And now we just need to find the total. It's the sum of these two. And there we have it. We need to calculate their magnitude, don't forget. We pretend that they're vectors, so we just use Pythagorean theorem. Make sure you break them into perpendicular components before you do that, though. So there's our magnitude. So that's what we did. We broke the secondary shear stresses into components, and we added those two things. So now that all the components lie on the three orthogonal directions, it's possible we could have some that are out of plane, but we don't in this case. We can calculate the magnitude just using Pythagorean theorem. Point being, break them into components and then use Pythagorean theorem. Then we compare against the allowable shear stress, and for fillet welds, it's 0.3 times the ultimate tensile strength. I think I stopped labeling steps. Determining the critical point, this here was step 5. This one here was 6, determining the magnitudes, adding them together as vectors, and determining the magnitude of the total, and then 8, compare the magnitude. I'm going to omit the bars. Well, we don't know what the ultimate tensile strength is. We're trying to find the ductile weld material that can safely support the load. So what we want to do is find out what ultimate tensile strength is required. We say SUT has to be greater than or equal to tau over 0.3. That's 28,000. And we have 95 KSI. And so the welding material that's the most ductile, that's going to be able to carry that, is an E100 series electrode. Because the lower the strength, typically, the higher the ductility. And that's confirmed here in this chart. On the upper end is the 16, is more elongation than the 120 series of electrode at 14.